Last time we talked about discs and we talked about washers. A shell is like a tall washer. Where like the washer, the thin part of the washer was like the cross section. A shell is like the opposite. I'll try to draw it the best I can, and we'll see how my drawing looks here in a second. But the idea with the shell is that the thin part is the face of the washer, and it's allowed to be as tall as it wants, right? This is like a shell, in contrast to try to draw another washer. This is my picture of a washer. So you can tell the difference between where the thin part is going to be. Let's call the thin part delta x for a little change in the x direction. And for our washer, the x-axis like poked through right here. This, being a shell, is going to be kind of oriented around the y-axis. And that means the thin part is once again delta x. So if I wanted to calculate the volume of a shell, what I could do is I could take the radius of the whole cylinder from the y-axis out to the outer surface, call that capital R, and take the radius just out to the inside of the shell, call that lowercase r. And that way my volume is going to be like a pi r squared times the height. We'll call this the height. Minus pi r squared times the height. Okay. So we're going to define a new variable that we haven't used yet. And this is going to be the midpoint between the capital R and the lowercase r. It's going to stretch right to the middle of this super thin area. And I'm going to call this rho, like the Greek letter rho. Because rho is like a Greek letter for R, and I've already used capital R, and I've already used lowercase r. And so we're going to just resort to using rho now. And it's the midpoint here. So now if I wanted to take my capital R, I could describe capital R as being rho plus delta x over 2. And my lowercase r would be rho minus delta x over 2, since delta x is the thickness. Capital R is half the thickness more, and lowercase r is half the thickness less than rho. And then let's expand this expression I have for the volume. When I FOIL this out, and for the moment, I'm just going to go ahead and factor out the pi and the h, right? Because that's the greatest common factor. But when I FOIL out these two things that are squared, the parentheses squared, I'm going to get rho squared plus 2 times delta x over 2, so just call that delta x, and then plus delta x squared over 4. And then this is all minus because of that minus sign. So then it's going to be minus rho squared. And this negative makes it minus 2 delta x over 2, which is just minus delta x. But then don't forget that there's also another minus sign we have to distribute, so that's still going to be plus delta x. And that's first, outer, inner. The last term is going to be minus delta x over 2 squared, which is positive delta x squared over 4, but then don't forget to distribute that minus sign one more time, and we get negative delta x squared over 4. Okay. It looks ugly, but things are going to cancel nicely, I hope. Yeah, so certain things cancel, and I'm left with 2 pi. Oh, and I forgot something. I've been making a mistake when I did my foiling. I forgot to put in some rows. This should be rho times delta x, and then this should be rho times delta x. Okay, and now I've got 2 pi rho delta x. And that's the volume of one shell. You're right. That should be pi h. 2 pi h rho delta x. I don't like the way I squeezed in that h. Let me try it again. It's going to be more convenient to name this volume delta V. The reason is because we're going to compose a bunch of shells together to make a certain shape, just kind of like we did last time with the discs and the washers. We were adding together a bunch of discs and adding together a bunch of washers to form a certain shape. And so we'll call that delta V because it'll just be one part of a collection. And so you can think of it as a small change in volume. But this is important. This is going to be important for just a minute here. Because in some cases, when we do volumes of revolution, meaning we take a curve, we revolve it around an axis, we've got a solid of revolution, we want to know what the volume of the solid is. Sometimes it's impossible to find the volume of revolution using the disk method, like we did on Monday. So instead we have to use what we call the shell method. For example, if we have the graph y equals x cubed minus x, x cubed minus x would look like something like this. And then the region bounded by this graph and the x-axis would be something like this. I'll color it in. And then we want to think about what we would get if we took these regions here and revolve them around the y-axis. And so it's going to be kind of like a donut, except there's not going to be really a donut hole. It's just going to be kind of pinched in the middle. And that's the solid we're trying to form. So if we were going to try to use the disk method, in the disk method, the sort of rectangles you draw over the region would have to be perpendicular to the axis of rotation. So in this case, they would be washers, right? Because there would be a hole in the middle of the disk, and you'd have, a face of the washer here and a face of the washer here, but there'd be a hole in the middle. So the problem with that is I would need a function to tell me how far away the inside of the washer is and how far away the outside of the washer is from the axis of rotation. In other words, to use like the washer method, we would take the pi times capital R squared minus lowercase r squared dx. And the lowercase r squared would be a function telling me how far away this blue curve is from the y-axis as a function of x. And then the, oh, and by the way, it wouldn't be dx, this would have to be a dy. Because if I'm making a washer here, these thicknesses of the washers would be little dy's. And then the capital R part would be this radius. And so I'd also need a function capital R of y to tell me what that distance is, and I would need a function lowercase r of y to tell me what that distance is. But remember, let me just write it down again, that this curve is x cubed minus x. So getting this lowercase r is trying to find an x coordinate given a y coordinate, but I can't find an inverse of this function, right? I don't know how, right? You can try your very best algebra skills to try to invert this function and get this equation solved explicitly for x. So you have x equals a function of only y. But I can't do it, I don't think it's possible. And so this is a situation where the washer method does not work just because we don't have functions capital R and lowercase r that do what we need the functions to do. And so we got to try something else. And now what we're going to do is the shell method. And the shell method says, all right, let's take vertical shells, right? And as I revolve this around the y-axis, it's gonna make a 3D shape that I can't draw very well. But these are going to be tall, and they're going to have very, little faces. It's going to be shells like I drew before. So that way the thickness of each cell is a dx. And the shell method says the volume of my entire solid revolution is going to be what it looks like to add up or integrate all of those shells. And the shells have, well, the shells have a volume of, what was it, 2 pi rho h delta x. And so the total volume is going to be the integral of 2 pi rho h dx. Because an integral, remember, is just a limit of a sum of a bunch of parts. And this is the way that we chunk it up into shells. Take the limit as the thickness of the shells goes to 0 and the number of shells goes to infinity. Now we've got to decide on a few things like rho is just going to be the distance from my axis of rotation to where the shell is. And that's just going to be the x coordinate of the shell, right? The x coordinate is the distance away from the y-axis. What is h? What's the height of the shell? Very good. Yeah. So the height of this shell is going to be the distance from the x-axis to the curve, x cubed minus x. Of course, since it's below the axis here, it's actually going to be negative, and so I should put a minus sign there to make it positive. But otherwise, yeah, exactly. This h is going to be something like x minus x cubed. So that way I can get this to be positive.
Are we currently finding it for like one of the sections, or is the shell method finding it for both sections at the same time?
Great question. So if I just do this integral from like x equals 0 to x equals 1 for this part, then this shell method is going to take care of the entire volume underneath the x-axis. But you're right that there's another region up here that needs to be rotated around. And I can get that either two different ways. Number one, I could just take this lower half and then multiply by 2. Or I could start my integral at -1 and go up to +1. And that way it would capture, oh, except it wouldn't capture both sides, would it? Because this is a positive above the x-axis stuff, and this is negative because it's below the axis. So if I took the integral from -1 to +1, I think that would actually cancel out. So what I need to do, I think, is just the integral from 0 to 1 and then multiply by 2. So yeah, to get the entire volume of revolution, I really need to multiply the integral from 0 to 1 by the number 2 to get the other half. So, good question. So setting up these problems is like more than half the battle. Like drawing the picture and figuring out what the integral has to look like is a lot of the work. After you do that, things go by a little bit faster, like 2 times 2 pi is 4 pi. And then distribute the x, so we get x squared minus x to the 4th. The antiderivatives just go by the antiderivative power rule. And then you just plug in 1s to get the answer here, which is 4 pi 1/3 minus 1/5. Oh, so your greatest common denominator is 15. So that's 5/15 minus 3/15, which is 2/15. And then 2 times 4 is 8/15. So it's 8 pi over 15. Sorry if I'm rushing through the integral part, but like I know you guys already understand the antiderivative power rule, and that should be like the easy part. But the hard part, or the new skill we're learning today, is how to set up the shell method integrals in the first place to get a volume of revolution. Are there any questions about that? How we did that? No? Yeah, so what I should say more explicitly is that this is the shell method formula. If you want to use the shell method, the volume is the integral from some lower bound to some upper bound of 2 pi rho h dx. And the way I remember 2 pi rho is it's like, that's the circumference of the shell. 2 pi r is the circumference of a circle. So you get the circumference of the shell, and then you have to multiply by the width of the shell, which is dx, and then you have to multiply by the height of the shell to get the volume, and then the integral means you're adding them all up. So you guys have this handout? The example we just worked was an example of using the shell method where we are rotating around or revolving around the y-axis. But if we had used the disk or washer method to rotate around the y-axis, the difference is now my disks or washers have a thickness of delta y instead of delta x. And in my integral, that becomes a dy. And remember, we couldn't actually do this method in the last example because we didn't know what the capital R and lowercase r functions are. So we had to switch. If you were using the x-axis to revolve your solid of revolution, then the disks would have a thickness of dx. And then if you're using the shell method and using the x-axis to revolve your solid of revolution, well then the shells would be laying on their sides around the x-axis. And if a shell is laying on its side, then the thickness of the shell is a dy. It's a change in the y direction. Does that make sense? Okay. So in some cases, it's possible to find the volume of revolution using either disk or shell methods, but the shell method may be easier. So here's an example. Find the volume of the solid formed by revolving the region about the x-axis. So we're going to use the two methods from the right side of your handout. It's going to be a horizontal axis of revolution, but we're going to do both. We're going to do the disk method and the shell method and see which one's easier. Okay, so with the disk method, we are going to take a look at this. And I always draw a picture before I start because just looking at the function is not very helpful for me whenever I'm trying to imagine how the disk is oriented and stuff. So I'm looking at a case where y is between 0 and 1. So let's call this 1 on my y-axis. And x is somewhere between 0 and e to the negative y squared. So when y is equal to 0, what's e to the negative 0 squared? 1. E raised to the 0 power is 1. So when y is 0, x is going to be between 0 and 1. And when y is equal to 1, this is going to be e to the negative 1 squared, or e to the negative 1, which is like 1 divided by 2.7, which is kind of like 1/3-ish. It doesn't have to be exact in my drawing. I'm just trying to get a feel for what this is going to look like in my drawing. So imagine I've got a graph that looks like that. Now x is this inequality. X is between 0 and this curve. And y is between 0 and 1. So I'm going to shade in the region that we're going to revolve. And I really recommend trying to draw these when you work through your homework. Might even ask that you draw these on the test question, because I think drawing it helps you understand it. And we're going to revolve around the x-axis, which means I take this and I go all the way around and I see what kind of shape I get. Now, to use the disk method, I'm going to set up an integral for the volume that looks like pi capital R squared minus lowercase r squared dx, because these disks are going to be shaped like so, where the thickness is dx. And then x is going from 0 to 1, it looks like. The only thing is, oh yeah, this is not a washer, so I don't even need that part. I only need the minus the smaller radius if it's a washer, but this is just a plain old disk. So what function is going to describe my distance from the axis of revolution? And it's actually a piecewise function. This is a piecewise function because if x were between 0 and e to the negative 1, then the function that tells me how far away my region gets away from the axis of revolution is just the number 1. It's flat on top. But what about in the other case where e to the negative 1 is less than x less than 1? What if I'm in that region over here? Then the function that tells me how far away this region gets away from x, my x-axis, my axis of revolution, that is described by this curve here. And that curve is e to the negative y squared. Right, we drew this curve here as x equals e to the negative y squared. Only this is supposed to give me capital R as a function of x. So I can't just write in this blank e to the negative y squared. That's not going to work. Instead, what I got to do is I need to invert this function. So that way I can write y equals the square root of, I don't know, how would I solve this equation? I would take the natural log of both sides to cancel out the e, and then I would take the negative of both sides to cancel out that minus, and then I would take the square root of both sides. So I'd say y equals square root of negative natural log of x. And that's what I plug in here. That's the distance, the y value, away from my axis of revolution, which is the x-axis, as a function of x. Okay, so I'm taking a pause for questions. Do you guys feel like you're completely lost? The first thing we did is we drew a little xy plane, and then we tried to figure out what this region looks like, where y is between 0 and 1, and x is between 0 and e to the negative y squared. So this curve is supposed to represent the place where x is equal to e to the negative y squared, and that's the upper bound on this region in my x coordinate. So then we filled it in, and we said, well, with the disk method, we're rotating around the x-axis. That means these rectangles, the cross-section of the disk is going to be perpendicular to the axis of rotation for disk method. And then the height of these rectangles, or the distance away from the x-axis, is going to be this capital R And that function changes based on whether I'm in this location, where it's flat on top, because y has to be less than 1, so I'm perfectly flat on the top, or if I'm in this location, which is greater than e to the negative 1, well, then it's not flat on top. Then it has a curve described by x equals e to the negative y squared. But I can't just plug in e to the negative y squared, because this is supposed to be a function of x. That tells me what y is. And so I take that curve, solve for y, and it's this solution for y that I'm going to plug in here. And of course, the y coordinate is going to tell me how far I am away from the axis of revolution. And since my integrand now of this integral is a piecewise function, we're going to have to split up this integral into two separate integrals. One is going to go from 0 to e to the negative 1 power, and that is going to be what in the integrand? Yeah. It's the first piece of my piecewise function, between 0 and e to the negative 1. The capital R function is just 1, and so you can write 1 or 1 squared, because we're taking capital R squared, but of course 1 squared is 1, so you got it. And then the second integral is going to be over the second piece of my piecewise function. And so this is going to be the integral from e to the negative 1 up to 1. And what's going to be in this integrand?
Negative ln of x.
Very good.
Because
Because you're squaring it, yeah. When we square the square root, it cancels, and we just get negative natural log of x. All right. The antiderivative of 1 is x. And if I have the function x as the antiderivative, and I plug in the upper bound and I plug in the lower bound and I subtract, it's just going to give me e to the negative 1. Next, what is the antiderivative of natural log? I'll take out the minus sign. Yeah, it's something like that. I don't remember exactly what it is, but you know you can solve for it using integration by parts. It's great if you remember, but I don't have that kind of memory. Instead, in integration by parts, we say u dv is equal to uv minus v du. I don't know how to take the antiderivative, but I can take the derivative. So that means u is equal to natural log of x. dv is going to be dx, so that v is equal to x, and du is 1 over x dx. So that way, I get uv minus the antiderivative of v du, which is x natural log of x minus x. I think that's what you said. So you were exactly right. I should have just trusted you. Here we go. X natural log of x minus x. And we plug in the upper bound and we plug in the lower bound. And we subtract those. All right. When I plug in the 1, I get x times, or 1 times natural log of 1 minus 1. What's the natural log of 1? 0. Any logarithm of 1 is always 0. Very good. So 0 minus 1 and then when I plug in e to the negative 1, this is going to be e to the negative 1 times natural log of e to the negative 1 minus e to the negative 1. What's the natural log of e to the negative 1? Negative 1, because the natural log and the e, they cancel each other out. They're inverse functions. So that's a negative 1 times e to the negative 1 minus e to the negative 1. Or I could write negative 1 over e minus 1 over e. So that's negative 2 over e, but then there's another minus sign, which makes it positive 2 over e. Subtract that 1, and then we multiply that by pi. So we get pi over e minus 2 pi over e plus pi, which is pi minus pi divided by e. Oof, a lot of work. It's definitely possible, but not something that you want to do. On the other hand, we were going to solve this problem using the shell method as well. And using the shell method, we say that the volume is going to be the integral of 2 pi rho h dx. Because with the shell, oh no, dy, I'm sorry. It's going to be a dy. Because in this case, if I'm revolving around the x-axis, my shells are going to have thickness dy like this. It's going to look like this picture on your handout. So the shells are going to have thickness dy's. You really have to have a great imagination to do calculus 2, right? Because like, you have to be able to look at those rectangles and think that's a cross section of a shell that's going to be revolved in space. And there's just not really a lot of good video animations of this stuff today, believe it or not. That could be somebody's capstone project in the future. Make them do video animations of this stuff. But anyways, this is the formula for the shell method for figuring out the integral. And since this is dy, I need to find a lower bound and an upper bound of my integral in terms of my y variable. What should be my lower bound? 0. An upper bound 1. Yeah, we can get that quickly just by looking at this. And then what is the function rho that tells me how far away my shell is from the axis of revolution? That's going to tell me how tall each shell is. But if I want to know how far the shell is away from the axis of revolution, this is just the y coordinate. Let me zoom into the picture. If I want to know how far this shell is away from the x-axis, that's just the y coordinate of where that shell is sitting. So we can say rho is equal to y, and then h is the height of the shell, and that's where the e to the negative y squared comes in. And this time, since I'm taking the integral with respect to y, it's okay that I have a function of y in my integrand.
Is it not
That's what we
piecewise
want.
this time?
It's not piecewise. Because when I integrate with respect to y, change the way you're looking at this, right? Like turn your head 90 degrees. And when I integrate with respect to y, I only have one continuous curve. So then my volume integral is going to be the one from 0 to 1 of 2 pi y e to the negative y squared dy. How do I solve this integral?
Integration by parts.
You don't need integration by parts this time.
U substitution?
Yep, you can do this with just a u substitution. What's my u going to be? Yeah, I could even do negative y squared if I wanted to. It's up to you how you want to handle that. But then du will be negative 2y dy. And I see a 2y dy here. I'm going to have to add the negative in myself. But this is going to be pi times the integral of 2y dy's du e to the u du. And I don't know if I showed you this, but what's going to be the new lower bound and upper bound for my integral? To get the new lower bound and upper bound, what you're supposed to do is plug in the old lower bound and upper bound into the definition of u. So like 0 squared or negative 0 squared is going to be 0, and negative 1 squared is going to be negative 1. This time it didn't make that much of a difference, but sometimes that matters when you're doing these u substitutions. And then the antiderivative of e to the u is, of course, e to the u. And then we plug in a negative 1, and we plug in a 0, and we subtract. And we get pi times e to the negative 1 minus e to the 0, which is going to be pi divided by e minus pi. The only problem is I forgot a minus sign somewhere. Whenever I swapped out the du, I should have put a minus here. So let's retry this, but with a minus sign. And then it would be pi minus pi over e. For my volume. So now you get to be the judge. Which method was easier, the disk method or the shell method?
Shell method.
Both were possible in that we got the right answer in the end. The disk method was possible, but there were a few difficulties. Like, number one difficulty was that this capital R function was piecewise when I look at it vertically. And when I had a piecewise function, I had to separate this into two different integrals so that I could integrate this part and then integrate that part separately. That was a little bit difficult. The second thing that was difficult about this disk method thing is that this piece, the square root of negative natural log of x, I had only found that after I inverted the function x equals e to the negative y squared to solve for y. And that adds a little bit of time, a little bit of difficulty, a little bit more opportunity to make a mistake. So that was something difficult. Another thing difficult was antiderivative of natural log. I didn't remember what it was. I mean, maybe it's not hard for Gwen, but for me, I had to do integration by parts to figure out that antiderivative. And then even just plugging in the bounds of the integrals and simplifying, that took a lot more work. Meanwhile, in the shell method, we didn't have any of those troubles. We just had a quick little u substitution, and then we were there pretty fast. So the first example that I showed you today, you had to use the shell method because there was no way to figure it out with the disk method. But there's other problems where the shell method is just more convenient than the disk method. And by the way, there's a lot of problems where the disk method is more convenient than the shell method. So the shell method is not like a one-size-fits-all solution, but it's the type of solution we're learning about today.
When you look at a problem, how do you know which one to try first?
It's a good question. Like for me, I'm not like a speedy math guy. Like for me, what I do is I just try one of them, and then if it doesn't work, I erase everything and I try the other one, you know. It's like integration techniques. If you try something and it doesn't work, you have to erase it and start over. If you're doing a U sub and you choose the wrong U, just gotta erase it and start over. Wish I had better advice, but that's how math goes 99% of the time.
Once you look at them, like once you start doing more and more problems, you start to see similarities between them.
Yeah, I mean, you could, as a rule, try to avoid piecewise functions. Like if you see that one method or the other is creating a piecewise function in your integrand, you might want to avoid that and choose the other method if possible. That could be a guiding principle. But use the shell method to find the volume of the solid formed by revolving the region about the y-axis. And by the way, this is not supposed to be the same problem. These are supposed to be 3 separate volumes. So in the first case, what if we want to revolve around the y-axis? Well then, x squared plus 1 looks like this. Because when x is equal to 0, y is equal to 1. And when x is equal to 1, y is equal to 2. So that's kind of what my picture looks like. It's a parabola, so it's going to be nonlinear there. And this is the region. And so we're asked to use the shell method and revolve this around the y-axis. So shell method. Are my shells going to be vertical or horizontal shells?
Horizontal.
These are going to be vertical shells. And the reason is because with the shell method, the shells are going to be parallel to the axis of revolution.
Oh, but in the disk they're perpendicular?
In the disk, they're perpendicular. So this time we're doing this bottom left corner, where we're taking a region and we're using the shell method to revolve around the y-axis. So it's going to be vertical. And if it's vertical, that means the thickness of the shell is going to be dx. So I'm using a shell with thickness dx. And the formula is going to be 2 pi rho h dx. Since I'm integrating with respect to x, my lower bound and upper bound of this integral need to be in terms of x. What are my lower bound and upper bound? 0 and 1. And then what is rho? Rho equals what? Perfect. Rho is telling me how far my shell is away from the axis of revolution, and in this case it's just the x coordinate. What is my h? Perfect. X squared plus 1. So before we solve that integral, and I know you could solve that integral, it's just powers, right? So you just have 2 times pi times x cubed plus x, and you can do that. In the interest of time, let's keep going, and let's talk about how to set up another problem where we rotate about the line x equals 1. So I'm going to put the line x equals 1 in red. And then I'll choose, I don't know, let's say orange for this example. So take this region and rotate it about the line x equals 1. And this is a slightly different problem from what we've worked in the past, because in the past we've always rotated or revolved around the x-axis or the y-axis. But we could take this shape and revolve it around x equals 1. When we do this, using the shell method, this is still a vertical axis of revolution. So my shells are still going to be vertical, because they'll be parallel. That means the thickness of the shells is still going to be dx. And so I'm going to write my shell method formula as being an integral of 2 pi rho h dx. By the way, my x coordinate is still starting at 0 and still ending at 1, because it's still the same region. X is still going to go from 0 to 1. H is the height of my shells, and that stays the same too, doesn't it? It's still x squared plus 1 to tell me how tall each shell is going to be. The only thing that changes is rho. This is the tricky part. Remember, rho is the distance from the axis of revolution to the shell. So what's the distance from the axis of revolution to the shell this time? One minus x. Now again, in the interest of time, we're not going to work out this integral, because once again, this is just a polynomial in the integrand. So you guys can do the antiderivative power rule, and you can plug in the bounds, and you can figure it out. But the new skill here is figuring out rho when the axis is not just the y-axis. In the blue, rho was x, because x coordinate told you exactly how far away you were from the axis of revolution. But this time, it has to be 1 minus x, because if x is equal to 0, 1 minus 0 is 1, and you are 1 unit away from the axis of revolution. And when x is equal to 1, well, then you're 1 minus 1 away from the axis of revolution, and you're right there. But you need 1 minus x to tell you how far you are away here. And notice we're going to get a different answer. It's not going to be the same volume, even though it's the same region. Which one's going to be larger, this blue volume or this orange volume?
I think the orange one.
Why do you think the orange one?
Well, when you rotate it, like the taller side would like have more of the area. Unless I'm rotating it wrong in my head.
You might be rotating it wrong in your head. I think you have the right idea, but if you have this blue one and you're rotating about the y-axis, then this taller part travels more distance.
On the outside, yeah.
But if you take this orange one and you rotate it around x equals 1, well then this taller part barely moves. It doesn't really travel very much. So yeah, this is actually going to sweep out a larger volume than that one.
That's so interesting.
Mm-hmm.
Like, I don't know, there's like a chemistry skill where you have to like see things on paper and make it rotate and do stuff.
Yeah. Well, and I haven't done this today, but we could put it into GeoGebra and we could see if it looks different. I just have to remember how to use GeoGebra, and I'm not even on the 3D calculator. How do I get to 3D? There we go, 3D. All right, what I want is the graph of x squared plus 1. So on GeoGebra, you have to type in t comma t squared plus 1. Oh, I forgot to type in curve. Okay. Curve of t comma t squared plus 1 comma t comma 0 comma 1. There we go. So that is my curve, y equals x squared plus 1. And we want to rotate this about the y-axis first. Oops. That's not what I wanted. What did it oh, it tried to rotate it around the x-axis. So let's not do that. Nope, 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 don't, no. GeoGebra can do neat things, but man, it is not user-friendly. It is so bad. All it wants to do is go around the x-axis. I thought for sure you could do this
like,
around the...
I think you could like manually edit and make it do the y.
Oh, maybe that's what I need to do. I just need to finish it. And then I need to go back to algebra, and then I need to say y-axis. Oh, what happened? No. This is what I'm telling you guys. It's not a friendly website. This website hates being useful. Okay. Nope. Okay, I clicked it and had my cursor there for a second. Okay. Yes. You got it. Thank you, Avery. Then, so this is obviously not the whole shape, right? The whole shape also involves a little line segment, which is going to be curve, where it's going to be curve of 1 comma t comma t comma 0 comma 1. Oh shoot, 2. There we go. Got it. And then we got to do this rotating again. We have to rotate it around the wrong axis first because it wants the x-axis really bad. And then I've got to change the x to a y. Haha. I guess it's one of those things, I should just be grateful that it exists at all. You know, I don't need to complain. But this is what it looks like around the y-axis. If I wanted to see what it looked like rotating around the axis x equals 1, that would be pretty impossible, I think, to do in GeoGebra. I think it only likes to rotate around axes. But instead, I could trick it by changing this from t squared plus 1 to making the x-coordinate t minus 1. Yeah, that's it. You just got to trick it a little bit. So this is what the shape would look like if we revolved around x equals 1, where the tall part doesn't rotate very much. It'll look more pointy. Okay. So the last thing we'll say is, what if I was going to rotate around the line x equals 2? Same shape, same region, x equals 2. Draw a quick picture. With it being the same region, it's still going to look exactly the same. Only this is my x equals 2 axis of rotation, so that when we use the shell method, we revolve like this. My entire region is farther away now than it was before.
Wait, does it make like a big hole in the middle?
Yeah, there's definitely going to be a hole in the middle. Yep. And to use the shell method, I'll set up an integral from 0 to 1 of 2 pi rho h dx, where rho is the distance from the axis of revolution out to where the shell is, and h is the height of the shell. Well, the height of the shell still hasn't changed. It's still x squared plus 1. The only thing that's changed, again, is what do I write down for rho this time? There you go. This time rho is 2 minus x, because the distance from this axis of revolution to here is 2 minus x. Distance is just a difference, and difference means subtract. So 2 minus x is the way to go. Is this going to have more volume or less volume than the last two?
I would say more volume.
Yeah, it's going to have a lot more volume, because the whole region is having to travel a lot farther through space. Let me see if I can trick GeoGebra into working again. So that's going to be what the outside of that region looks like. The inside is going to be a whole thing to try to make it work, because the inside would have a radius of 1. So I would need to take this line and rotate it around the y-axis to get that working. And it's not going to let me rotate around the y-axis, so instead we rotate around the x-axis. Let me go and we change it. There you go. So yeah, there is a hole in the middle of our solid of revolution there. But it's a lot bigger.